Today's video is composing functions to graph more complicated functions. With this warm-up, we're going to talk about composition with numerical values, and this is something that we learned last year, so we'll just review it. Here are the four answers. But if I have f of g of 0, what I would do is find g of 0, which is 5, and then replace g of 0 with 5. So now f of g of 0 becomes f of 5. And then I look at the table, and f of 5 is 9. So once again, g of 0 was 5, and then f of 5 is 9. And we would do a similar thing for all of these. I would find f of -1 first, and then that is -3. So then I look at g of -3, which is 8. Likewise, if I have f of 2, I would find f of 2, which is 3, and then find f of 3, which is 5. Likewise for g of -1, g of -1 is 6, and g of -1 means g of 6, which is 1. So now what we're going to do is do the same type of thing. And we're going to decompose a more complicated function into its smaller parts. So first, if I want y equals 1 over the absolute value of x minus 2, all of that minus 1, the first thing I might do is think about the graph of y equals the absolute value of x minus 2, which I've already graphed for us. So if we think of this as f of x, then what I have in step 2 is 1 over f of x. So what I would do is I would take every single y value here along each of these spots, and then I would take the reciprocal of each of these y values in step 1. So the reciprocal, let's just start at x equals 3. When x equals 3, y equals 1. I would take the reciprocal of that because I'm just going to do 1 divided by this. Well, the reciprocal of 1 is 1. Now let's look at 4, 2 on the original graph. I would take the reciprocal of the y value, so 4, 2 becomes 4, 1/2. And then 5, 3, I take the reciprocal of the y value, that becomes 5, 1/3. Now if I look at x equals 2, that's 0. Well, then I take the reciprocal, 1 divided by 0. That's going to be undefined. So I'm going to end up with a vertical asymptote, which makes some sense because if I think about what would happen at x equals 2.5, I have y equals 1/2. Well, the reciprocal of 1/2, 1 divided by 1/2, is 2. And so on. What I'm going to end up with is something that looks curved, has a horizontal asymptote at 0, and a vertical asymptote here at 2. And then I have something similar happening, except it's in the negative world. So down here, if I look at 1.5 for x, I would end up with -1/2 for y. The reciprocal of that is -2. 1, -1 becomes 1, -1. 0, -2 becomes 0, -1/2. -1, -1 becomes -1, -1. -1.5, -1/2 becomes -1.5, -2. And what you can see is something that appears to be going off toward these asymptotes. which again makes some sense because when y equals 0, if I take the reciprocal, I'm going to get an asymptote. And then likewise, if we look at this side of the graph, all of this part is going to match up identically with this part, and I'm going to end up with something that has a horizontal asymptote at 0 and a vertical asymptote at x equals -2. Then finally, I'm going to take step 3, which is graphing the exact same function. So if I call this function g of x, what I'm going to do is take g of x and subtract 1. So all that's going to do is decrease every y value in step 2 by 1, because I would take g of x and then subtract 1. So all of these things are going to just get subtracted by 1 in terms of their y values. I'm still going to have the same x values for vertical asymptotes. I'm just now going to have my horizontal asymptote at -1. So it's going to look something like this. So essentially what's happening is you take each step and then we look at what the step was, and then we figure out what we're doing to the y values in the previous step. So if I look at the domain, that would actually be an x value radar detector. That's my fault. And it hits every value except for x equals -2 and 2. So that's -∞ to -2, union -2 to 2, union 2 to infinity. Problem 2, similarly, I'll take y equals the absolute value of x minus 2, which I've already graphed. I don't really probably need to do this because this part is actually easy enough, so I can probably just start here. Then what I'm going to do is I'm going to take the square root of this. So that means all I'm doing is taking the square root of every y value in step 2. So if I consider this to be, let's say, h of x, what I want to do is take the square root of h of x, which is taking the square root of every y value from step 2. So at x equals 2, y is 1, the square root of that is 1. At these two values, the y value is 2. The square root of that would be the square root of 2, which is about 1.414. But more importantly, maybe we should look at things that are easy to take the square root of. So if I look at where y equals 4, I'm going to use these x values at 5 and -1 to give myself a y value of 2. And then it'll be easier to connect them in curvy ways. So it kind of looks something like this. We're going to do the same thing with domain. If I look at this, it appears that everything's getting hit. So it's -∞ to infinity, which should make sense because there's no x value that I can plug into this function that has any sort of problems. Number 3, let's graph 1 minus x squared. So that's going to have -x squared moved up by 1. Now I'm going to take the reciprocal of that. So I take the reciprocal of every y value in step 2. Once again, remember that if I get zeros, those are going to be vertical asymptotes if I have a reciprocal. And as I get closer to them, my reciprocals actually get bigger. So it's going to be something that looks very curvy and going off to infinity. And then these values, if I look over here, -2 and +2 for x are at -3. So I know that that's going to be at -1/3 when I take the reciprocal. It'll look something like this, because as it goes off to -infinity, my y values for the reciprocal are going to be close to 0. So the domain, if I do an x radar, would be -infinity to -1 union, -1 to 1, union 1 to infinity, which, if you think about how you would solve this algebraically to figure out where the denominator is equal to 0, which would be a violation, you have x squared equals 1, which gives you x equals ±1 are the problem areas. Now try this on your own. Pause the video, and then I will show you the answers. This problem is actually a little trickier than you might think. So you end up with absolute value of x -3, pretty straightforward. Then you do the reciprocal of that, which we've practiced a couple times, so that's pretty straightforward. But then when you take the square root of step 2, if you take the square root of that, we have a lot of negative numbers in between -3 and 3 for the values of x. We have a lot of negative y values. And when you take the square root of any negative y value, we get something that does not exist in the real numbers. So the entire middle portion of this graph no longer exists. That all goes away because there are no negatives allowed inside. So if we look at what is allowed, we just have all of these numbers, which when you take the square root of them, it's just going to flatten the curve out a little bit. But the curve above the y-axis still exists. So the domain here is -infinity to -3, union +3 to infinity. There's a whole lot missing in the middle. Part 2, we're going to graph some of these. So if I take absolute value of x and then do the function value of that, let's quickly make a chart. So if I just look at some of these values, when x is negative, that changes what happens inside the absolute value to a positive number. But everything that's 0 or positive, the x value remains the same. So therefore, if I look at f of x, I'm sorry, not f of x, f of the absolute value of x, essentially what I need to do is take the function value of what I'm highlighting. Then after I take the function value of what I'm highlighting, then what I'm going to end up putting inside on my graph are these points. So this middle step is just a way to get me to understand what points I need to put on the graph. So what I'm going to do is, what is 2 on this graph? 2 is at -2. When I have x equals 1, that's at -2. When I have 0, that's at -2. 1 is -2. 2 is -2. X equals 3 is -1. X equals 4, 0. X equals 5, 1. So I'm going to plot all these points. And what I see is when I take the absolute value of x and then do the function of what's happening there, everything that's on this side of the graph is going to get mirrored over to the other side.
Now, why does it stop? It doesn't continue because there are no function values past -2 for x. Now, let's just say, hypothetically speaking, this went on. What I would have done is when I plug in -3, I would get 3, and then that would give me -1, and it would continue. However, because these values were not originally in the function, I can't graph those in my new function because I can't invent new domain values for x. So what f of absolute value of x is going to do is going to mirror the function on the right over the y-axis to the left. So everything over here that I highlighted in blue is going to get mirrored over as long as there was an original point in the function that had that. Letter B is a lot easier for us to understand because we're just taking the absolute value of f of x. So what would happen if I take the absolute value of f of x is I just take the absolute value of whatever the y value is. And so what's happening is anything that was above the axis stays above the axis, and anything that was below the axis gets mirrored up and mirrors over, kind of like when I have y equals the absolute value of x. Anything that was below the axis gets mirrored up. So when I have absolute value of the entire function, anything below x-axis gets reflected to be above it. Now, one thing you notice when you do this is that nothing up here got replaced. I just mirrored this part over, and it ends up showing up here. However, when I did absolute value of x on the inside of the function, stuff got eliminated. All of this went away. And that's because functions don't have to pass the horizontal line test. And so because of that, all of these things are going to get eliminated when I mirror something over the y-axis. But anything that gets mirrored over the x-axis will never have anything to replace because there's nothing up here. Now if I take the absolute value of this f of x plus 1 minus 2, what I have to think about is what's actually happening. So the x's are getting subtracted by 1, the y's are getting absolute valuized, and then subtracting 2. So I'm going to take all of my x values, I'm going to subtract 1, and then I'm going to take this function. It may actually even be easier to kind of think about it as a picture. So if I take this absolute value graph here, then what I can do is I can take this picture and then if I move it down 2, that'll take care of everything that happened with the y's. Then I can just move it to the left 1, and then that will actually be exactly what happens to every point.